Today we're going through chapter 1 and chapter 2. That's based on the materials that I gave you, which are part of our first session, which are part of session 1. So in session 1, these resources are available to you. Chapter 1, chapter 2, units of measurements, and also intro to electricity, charge, and measurement. So I'll start by going through chapter 1. All of this is for the next course, which is called Principles of Electrical Circuits 2. Another set of electronic components we have are active components, such as transistors and integrated circuits that we use to amplify signals. All right, so let's begin. What are the SI fundamental units? We have length, mass, time, electric current, temperature, luminous intensity, and the amount of substance. So the SI fundamental units are units that were agreed for the SI system. The standards were set. And so the unit of length is the meter with a symbol M. For mass is the kilogram, kg. For time is second. For electric current is the ampere, which we're using. So this is the fundamental unit. For temperature, Kelvin, chandelier, the mole, and so forth. Okay, what are some important electrical units? So of course, when we talk about fundamental units, we have the base units, which are the 7 that we discussed earlier, and then we have other units that are derived units from these fundamental units. Except for current, all electrical and magnetic units are derived from the fundamental units. So what are some other electrical units? We have electric current, we have charge. Remember we said that electrons have a negative charge and protons have a positive charge. The unit for charge is actually the coulomb, right, with the symbol C. We have voltage, and the unit for voltage is the volt with the symbol V. We have resistance. The unit for resistance is the ohm, and also we have power. The unit for power is the watt. And so we'll be discussing all of these units right here. We'll be calculating them, and essentially we are going to be more familiar with them by the end of this course. Here we have some other units that are more on the magnetic side. I said before in the start of the class that the electricity and the movement of electrons is very much related to magnetism. And so here we have some magnetic units. We have magnetic field intensity H, magnetic flux, and the unit is the Weber. We have magnetic flux density, the unit is the Tesla. Magnetomotive force, the unit is ampere turn. We have permeability and reluctance. Now all of these principles are used in the design of motors and the design of generators, which are electronic devices. And so this is one area where you can see the correlation between magnetism and electricity. All right, let's just review scientific and engineering notation. So again, these two methods are used to represent really large numbers. I know you guys are familiar with this. For the scientific notation, we only use one number after the decimal point, and everything else is placed after the decimal point. And then whatever the power of the highest number, we raise it to 10. For engineering notation, we use multiples of 3. So it's going to be 10 times 3 to the 0, 3 to the 3. And that's how we end up with the suffixes and the prefixes such as kilo, mega, giga, etc. So again, here are some examples. We have a very small number, and we write in the scientific notation is going to be 2.7 because we only use one number, times 10 to the minus 5. So you can see we move this 1, 2, 3, 4, 5. Okay, my pen is not working properly. Guess it just wants me to be slow. All right, and now for engineering notation, since we only use multiples of 3, instead of having 5, we move it 1 up, and then we have minus 6. Again, another number, 0.605 times 10 to the minus 1 is going to be 6.05 times 10 to the minus 1 for scientific notation. And for engineering notation, since we use indices of 3, we make it 605 times 10 to the minus 3. Again, this notations for engineering notation, we use some prefixes such as kilo for thousands or 10 to the 3, mega for 10 to the 6, giga for 10 to the 9, tera for 10 to the 12, peta for 10 to the 15. Likewise, on the small side, we use milli for 1,000ths or 1 over 1,000, or 10 to the minus 3. Just give me a second, let me plug in my computer. Maybe that's why. All right, there we are. So again, we have micro for 10 to the minus 6. This is 1 over 1 million. We have nano, 10 to the minus 9, pico, and also we have femto as well. So again, these prefixes help us to express really large numbers. Instead of saying all the numbers, we can use the engineering notation. We can use the prefixes to describe them very easily. It also helps us in reducing errors as well. Okay, so again, oftentimes in our calculations, it's important to convert units, and so we need to have an understanding of the prefixes and the suffixes so that we can go ahead and convert them successfully. So again, you see here 4.7 kilo. This is the same thing as 470,000. Now a mega is going to be a million, so this is going to be 0.47 mega. When converting from a smaller unit to a larger unit, move the decimal point to the left. Remember, the larger unit means the number must be smaller. Again, anytime we convert to a smaller unit, then of course our number is going to be smaller. So if you have say you have 1 ohm and you want to express it in milliohms, it's going to be 1,000 milliohms. Likewise, if we're going from milliohms to ohms, our number is going to be small as well. Any questions so far? This is not new. It's something that you have been using. It's something that you will continue to use for the rest of your career. Any questions so far? No problem. If you're at work, that's fine. So I'll just keep going. If you have any questions, feel free to interrupt me. All right. So again, it's important that you understand the prefixes and the suffixes so that you can calculate things correctly. For example, if you see this 10,000 ohms plus 22k ohms, the answer is not, you don't just add 22, but you need to acknowledge that this k means 1,000. So this actually means that this is 22,000 ohms. And so then you can add them together, it becomes 42,000 ohms. And you can express this as, again, k means 1,000, so it's going to be 42k ohms, right? So when you look at numbers and any problems we have, we need to make sure we look for the suffixes and the prefixes so that we are able to avoid errors by acknowledging these and adding them properly. If you don't add them if you don't acknowledge the suffixes and the prefixes, you will have errors. All right, let's continue. Okay, what about addition? If you're going to add two numbers here, say we have 200 microamps and 1 milliamp, we cannot just add these together. We need to put them in the same prefix or the same suffix to add them. So again, this is going to be, we know that 1 milliamp is equal to 1,000 microamps, right? We know that. So this can be, we can say that this is 200 microamps plus 1,000 microamps, which will give us, okay, this is incorrect here. You can see it's incorrect. 1,000 plus 200 is not 12,000. Tripping. So this is 1,200 microamps, right? And so this gives you, and if you want to convert this back to milliamps, it's going to be 1.2 milliamps. So this is one way you can do it. The other way is to convert this to milliamps. So this will be 0.2 milliamps. And now when you add them together, you get 1.2 milliamps. So again, in multiplying and subtracting, we need to notice the notation of whatever we're working with and convert them so they can have the same notation so we can avoid errors. One way to do that is to just put it in your calculator. So in your calculator, you have this function or this button called EE, and you can use that to actually put in the notation. So in your calculator, you can put in 1.0 milliamps plus 200 microamps, and you're going to get the correct answer. That's when you do it in your calculator, because your calculator will evaluate this as milliamps, it will evaluate this as microamps, and it will give you your correct answer in amps. All right? When you're doing it yourself, we need to be mindful of this so that we avoid errors. Okay, what is significant figures? This significant figures helps us to reduce errors in our work. All right. What are the rules for determining how many significant which figures are significant? Non-zero digits are always considered to be significant. Zeros to the left of the first non-zero digit are never significant. Zeros between non-zero digits are always significant. Zeros to the right of the decimal point for a decimal number are significant. Zeros to the right of a decimal point for a whole number may or may not be significant depending on the measurement. So significant figures helps us to reduce errors in our calculations. All right, so let's have a look at this. It says, look at the rules and determine how many significant figures are in each example. So if you have this number here, you're told how many significant figures? Okay, we have 5. If we have this number here, how many significant figures do we have? So we have 3 significant figures here. The zeros are not considered to be significant. In here, we have how many significant figures? 4. The zeros in between are also significant. In this case here, how many significant figures? We have 4. If you guys are doing drafting and design, you know that the number of zeros you have determines your accuracy, and that also, based on whatever you're drawing, it helps with the tolerancing of your drawing, of your design, of your part. And so these would be significant as well. So in other words, if you have 5.1, is not as accurate or it's not as precise as 5.100, right? This says that this is precise down to the thousands, right? This one is precise only to the tens. Zeros to the left of the decimal point with a whole number may or may not be significant depending on the measurement. So again, here we have 5100 or 5100, and we're saying that we have 2 significant figures. Okay, so we have a small quiz before we go to the next one. It says a resistor is an example of a passive component. The electrical unit that is fundamental is the ampere. That's for current, right? In the scientific notation, again, scientific notation, we only take one number and the decimal and whatever it is, right? So what is this written in scientific notation? We're going to take this 5 here, we're going to move it 1, 2, 3, 4. So this is going to be 5.6 times 10 to the 4, which is this one right here. In engineering notation, what is this one? Again, so this is going to be 5. So again, we need to have, and this is a free, so that's 0, 3, 6, minus 6, whatever. So this is going to be, okay, so just a second, this is not correct. Since we are moving this forward, it's going to be negative. So this should be minus 4 and not positive 4. So this is not correct, this is correct. Let's look at this one as well. So same thing for this one, but now we need to have an indice of 3 or 6. So let's go 1, 2, 3, 4, 5, 6. So we can do 6 here, and it's going to be 560 times 10 to the minus 6, right? So we can write it this way, 560 times 10 to the minus 6, or we can write, we can move it 1, 2, 3, and it's going to be 0.56 times 10 to the minus 3. So this option is here, and we can use that. Right, so again, it's just a matter of you moving. So if we had another example, so for example, we had 0.00016, right? If you write this as milli, because this is what it is, this is 56 milli or 560 milli. If you write this as milli, it's going to be 1, 2, 3. So it becomes 0.16 milli, right? Which is 0.16 times 10 to the minus 3. If you write it as micro, it's going to be, you're going to go to 6 like this one. So we move 1, 2, 3, 4, 5, 6. So we had the foot point here, so we write 1, 6, and it becomes 160 times 10 to the minus 6. All right, let's continue. Again, what do the prefixes mean? So of course, this one means milli. This one means micro. This one means nano. This one means pico. So they're not hard to remember, just take a look at them. The prefixes pico, what does pico mean? Okay, this is pico right here. Then we have 2700 megawatts. How can we write this? We can write this as, if we write it as kilowatts, it's going to be 2.7 million, right? Okay, hold on. So 2.7 megawatts. We can write this as gigawatts. It's going to be 2.7 gigawatts. Mega is 10 to the minus 10 to the 6, which is million. So it's going to be 2.7 gigawatts. All right. If you wanted to write it as kilowatts, we need to, instead of it being, we need to essentially multiply it by 1000. So it's going to be 27,000,000 kilowatts. All right. Of course, milli is going to be much larger. Terawatts is 1 after giga. So for terawatts, it's going to be 0.0027 terawatts. Okay. Understanding the prefixes that this is 1000. This is going to be, this is million. Okay, this one is a million and this one is 1,000 million. All right. I think we're coming to the end here. It says the value of 60. So again, 68k. What is k? This is the same thing. K is 1,000, so this is 68,000. All right. How can you write this? It says, what is it equal to? Of course, it's equal to this. You can also write it as what? If you wanted to write this as mega, mega is going to be 1 million. So this is going to be 0.068 mega ohms. All right, because to get to mega, you need to move it up. So this is for mega ohms here, and if you were to write it in terms of ohms, it's going to be 6.8 times 10 to the 4. That's fine. So this is K, 6.68K. Again, 68 kilo ohms is the same thing as 68 times 10 to the 3. Now, if you wanted to write it as 10 to the 4, it's going to be 6.8 because you move this one back one place, all right? And you put the decimal point here. So you're going to have 6.8. Since you move it back, this one increases by 1 times 10 to the 4. So this is also correct. Okay, now we're gonna add this too. So again, like I mentioned to you, if you're gonna add two things, they need to have the same indice, right? So either you put both of them in milliwatts or you put both of them in watts. So again, how do you get this to be watts? So you 1 milliwatt, 1 milli is the same thing as 0.001 watt. If you keep that in mind, that really helps. So if 1 milliwatt is 0.11 watts, so guess what? This is going to be, if 1 is here, this is going to be 10 watts, right? If 1 is here, it's going to be 10 watts. If 1 is here, it's going to be 100 watts. And so we see 300 watts, so we know already that this is going to be 0.330 watts. So if you add the two together, of course, we get 1.830 watts. Right? This is what we have right here. So again, to add these two, we need to either put everything in milliwatts or put everything in watts. If you wanted to put this one in milliwatts, it's going to be 1,500 milliwatts. And if you add the two together, you're gonna get 1830 milliwatts, right? Which is the same as, because this relationship is true, 1 milliwatt is equal to 0.001 watt. And you need to practice this because some units we use for our circuits are really large and some are really small. And so instead of saying the whole number all the time, we will use the indices definitely to communicate that information. So for example, you went to the power company. When they talk about how much power they generate, they're not going to talk about, okay, we generate 200,300. Okay, let me give a practical number. They're not going to say, well, we generate 200,000 volts and whatnot. No, they will use the indices. They will use kilovolts, megavolts, and if they talk about the current, they're going to use, mega amps or whatever. However much current they use, the language of the industry is using those indices, right? Using kilo, mega, milli, and so you need to have an idea. You need to understand them so you can also talk the language. Now in this course, we're going to use that language as well. When we describe circuits, we're going to use milliamps and so forth. So you need to familiarize yourself with them and doing conversions. Now we do have one exercise that helps you with that. I think it's a worksheet. All right, let's continue here. I think this is the last question. It says the quantity 200 microvolts. Again, what is micro? You need to know, okay, when you see that micro is equal to 10 to the minus 6, right? What does this look like? So 1 micro, what does 1 micro look like? Is equal to 0.000001. If you look at this position here, this is the 6th position, yeah? So this is 1 micro. 1 micro is equal to this. So you have 200 micro is the same as what? So let's write 200 micro. 200 micro is equal to 0. So this is 1. So this is going to be 10. This is 100, right? So my 200 will be right here. 0.0002. That's it. 200. I can use 2 or let's put 200. So I put volts here. Okay, so again, 200 microvolts is the same as 0.000200 volts. That is important to keep in mind. So this is correct here. Okay, it says 200 microvolts is the same is the same as 20 millivolts. This is not correct. What is 20 millivolts? 20 millivolts, 1 millivolt is equal to what? Okay, let me just tell you. 1 millivolt is 10 to the minus 3, right? It's 20 times 10 to the minus 3 volts, which is the same as 0.020 volts. That's 20 millivolts, so it's not the same as this, right? What about 0.2 volts? This is the same as 200 millivolts. So 0.2 volts is what? You can write it as 0.200 volts. And what is that? That is, if this is 20 millivolts, then this must be 200 millivolts, right? So again, you can write this as 200 millivolts. It's going to be 200,000 microvolts. So they're not the same. This is the only correct answer here. So again, we just need to practice this. It's not something that's difficult. All right, let's go on to the next presentation. Let me close this one. Let's go to the course and take this one. I think I downloaded it already. All right, let's look at the second presentation. Here we talk about the atom and stuff like that. So again, we're going to go through this very quickly because it's something that you know already. Okay, so we have the Bohr's model. The Bohr atom is a tool for visualizing the atomic structure. Okay, so again, talk about the nucleus. We say that it is positively charged. Okay, nucleus is positively charged. Okay, hold on. Put some definitions here. We have the nucleus. Positively charged. Why? Because all the protons are there and the neutrons are there and they are compact. They are compacted together. Then we have the electrons. The electrons go around the nucleus in different orbital shells, right? So again, we have 2 shells, 2 electrons in the first shell and so forth, 8 in the next shell and so forth, right? The atomic number is the number of protons, and it also determines the particular element, right? So each element has a certain number of protons. In the neutral atom, the number of electrons is equal to the number of protons. Okay, that's the neutral atom. No questions about this. So again, you also should know that the electrons have a negative charge, the protons have a positive charge, and we talked about the attraction yesterday, right? Some time ago, we talked about the attraction between the positive and negative. So the electrons are attracted to the nucleus. That is why they keep in orbit. We also said that the further it is away, we have less attraction, right? So we have less attraction here because of the distance, and that is why we talked about free electrons and electrons gaining energy and leaving the atom. Let's continue. The outer shell, the last shell, we said this is the valence shell, right? So the valence shell is what is involved in most reactions. And this is what accounts for electrical and thermal conductivity, and we talked about that as well. Anytime we have a reaction, we are dealing with the electrons on this valence shell. So this is silicon, and there are 4 electrons on the valence shell for silicon. Right? Silicon is considered a semiconductor, and we'll see why. Because we can actually add electrons here and cause this to have a net negative charge, or we can actually subtract electrons and cause it to have a net positive charge. This semiconductor material. Okay, there is a force between the charges. Very quickly, again, this force says that the charge is proportional to it says that the force is directly proportional to the charge, right? The force is proportional to the charge, and the force is inversely proportional to the distance, to the square of the distance, right? The force is inversely proportional to the square of the distance. What does that say? It says that the force is proportional to the charge. Like charges are going to repel. Okay, hold on. They are going to repel each other. And we are saying that the further, and of course, unlike charges are going to attract. And we're saying the further the distance is, the force that is attracting them together is essentially based on the distance. So the further the distance, the less force of attraction we have. That is why we are able to have free electrons. Let's continue. Voltage is the energy. So we start with some definitions here. What is voltage, right? These definitions you need to memorize. So if I were you, I would make a card and put in my notes, hey, what is voltage, and be able to memorize it and know it so that you can use it for your calculations. Voltage is the energy per coulomb of charge that is responsible for establishing a current. So another way to say that is voltage is the energy that is available, or the energy that is used for every coulomb of charge that is flowing, right? Work is done as charge is moved in the electric field from one potential to another. And again, when we talk about charge moving, right, the carriers of charge is actually the electron. So as the electron moves, you have the negative charge moving. And again, depends from where it's moving from. If it's moving from a neutral atom, we have a positive charge being created, right? Because we have a positive ion being created. So work is done as charges moved in the electric field from one potential to another. Voltage is the work per charge done against the electric field. Again, work per charge done against the electric field. Again, a way to remember voltage. Voltage talks about the energy that is available for each coulomb of charge that flows. So if you have a battery, right, and your battery can supply X amount of energy, joules of energy per coulomb of charge that flows, that will be the voltage of the battery. Now, when you actually connect the battery to a circuit, right? Then the battery is going to cause the electrons to flow, correct? And then that will be the voltage across whatever component that you have. So it has to do with your energy that is available for every coulomb of charge that flows. Now, when we talk about charge flowing, we're really talking about electrons moving, because electrons are the charge carriers. So 1 volt is the potential difference between 2 points when 1 joule of energy is used to move 1 coulomb of charge from one point to the other. Again, when 1 joule of energy is used to move 1 coulomb of charge from one point to another. In other words, 1 volt is available when we can use 1 joule. 1 joule is available for 1 coulomb of charge. Okay, 1 coulomb. Let's continue. And again, this definition will come up again. I have some other handouts that I gave to you where you can find similar definitions for voltage and for current and for resistance and so forth. I have a class now, so I can come back, yeah.
Encourage some students to come to safety engineering.
Okay, I will do that. Okay, so again here, let's have a look at the battery, right? So we have remember we talked about the battery, that we have a reaction going on here, and we call it a redox reaction. Right? And we said, based on this reaction, we have some electrons being given off, right? Some electrons are produced, and most times this electrons at a high energy level. Okay, so voltage is responsible for establishing current. Like we said, voltage sources include generators, solar cells, and batteries, to name a few. So here we have the copper zinc battery. The chemical reaction occurs when there is an external path for the electrons. So we have an external path for the electron, which is the wire right here. And you can see here that the electrons that are produced from this reaction, right? We have zinc 2 plus 2 electrons being produced. These electrons travel over the wire and they come into this copper electrode right here. And then of course we have the salt bridge here where we have the compounds are able to go across to the next solution. So again, most of the batteries we have a reaction happening, and only when you connect the battery to a particular load, this is when electrons are going to flow from that battery based on that reaction, and the reaction will continue generating that current. Again, you'll learn more about this as well. The important thing I want you to get right now is that electricity is based on the movement of electrons. And of course, with the battery, we have a chemical reaction that produces electrons. And of course, these electrons convert the energy into other forms of energy that we can use. Batteries do not store charge. They store chemical energy that can be converted to current when an external path is provided to allow the chemical reaction to proceed. Rather than saying charging a battery, it's more accurate to say reversing the chemical reaction on a battery. Now we have fuel cells. Of course, you guys are following the revolution with the electric vehicle and with decarbonization. That is one option that is there as an alternative to fossil fuels. A fuel cell is a device that converts chemical energy into a DC voltage directly by combining a fuel, usually hydrogen, with an oxidizing agent, usually oxygen. The hydrogen and oxygen react to form water. The process differs from batteries in that the reactants constantly flow into the cell where they combine and produce electricity. So again here, using a fuel, hydrogen, using oxygen, we have that reaction happening, and of course the fuel cell gives off electrons, and these electrons, as the electrons move, right, they then can power load. So we will see that current, when we talk about electric current has to do with the movement of electrons, how many electrons are moving in a particular amount of time. Voltage tells us, okay, what is the energy that is available for every coulomb of charge. For voltage tells us what is the energy available for the amount of electrons that are flowing, for the charge that is flowing. So let's talk about current. Current is the amount of charge. So again, what has the charge? Electrons have the charge. Current is the amount of charge that flows. Again, the charge of each electron is measured in coulombs. Current is the amount of charge that flows past the point in 1 unit of time, right? So that time can be 1 second, etc., etc. 1 ampere is the number of electrons having a total charge of 1 coulomb that move across in 1 second. So if you want to say we have 1 ampere of current, this is when we have 1 coulomb of charge flows past the point in 1 second. We say that this is 1 current. So we see again, current is the rate at which the charge is flowing. So what if we have 2 coulombs passing in 5 seconds? Of course, it's going to be 2/5. And that gives us a current of 0.4 amps. Okay, you have to keep that in mind. That will come up again, that current is the rate flow of charge. How much charge is flowing per unit time. So if you're given the charge and you're given the amount of time, you can calculate the current. What is resistance? Resistance is the opposition to the flow of current. So like we see that the battery causes electrons to flow in the circuit, well, we can actually measure the opposition to that flow of electrons. And of course, some materials, based on their composition, they are good conductors, some are good insulators. Now, resistors are devices that are manufactured to have a particular amount of resistance. So the unit for resistance is the ohm. And we can say that we have 1 ohm of resistance when we have 1 ampere flowing when 1 volt is applied. So if you apply 1 volt and we get a current of 1 ampere flowing, then we say that the resistance is 1 ohm. All right, and that gives us Ohm's law. So if we have 1 volt flowing and we have 1 ampere of current, then we say that we have 1 ohm of resistance present, and we'll say that this is called Ohm's law. So there's one way to describe resistance. We can describe it with R. We can also describe the reciprocal with called conductance. So whereas resistance is the opposition to the flow of current, conductance tells us how much current is flowing, and conductance is 1 over resistance. So this chart here is normally used to identify the resistors. So the resistors that we use, like some of them, they have color bands on them, and the color bands is almost like a code to help you identify the resistor without having to measure the resistance of the resistor. So again, you have a number of bands, some of them representing numbers, and we have some representing the tolerance. Now, tolerance talks about the manufacture process of the resistor. As you know, nothing in this world is perfect, right? Anything you manufacture, anything you cut, anything you design, you need to have some tolerance as to, okay, what tolerance can I manufacture this with and it will still work? So too with the resistors, when they are manufactured, it's not a perfect process, but quality control uses the tolerance figure so that the values are within that range. So what does that mean? If you manufacture a 5.1 k ohm resistor and you have a tolerance, the process has a tolerance of 5%, it means that if you measure this resistor, the resistance can be 5% higher than this one or 5% lower than that one. If we do, let's do this first example. So if I do 5.1k times 1.05. Now this 1.05 is the same thing as 5%. Oh, sorry, 105%. So say 5.1 times 1.05. And so that gives me 5.335. So I can say that the highest value is going to be 5.335K. Likewise, if I measure this, the lowest value is going to be 95%. 5.1K times 0.95. Which is going to be 4.845. All right. So again, this is important because, like we talked about, when you design, if you design a circuit for a real world application, tolerance is important because you need to know, okay, how precise does my circuit need to be to function properly or to function safely. And again, this tolerance comes because of the manufacturing process, right? All right. Again, also the colors on the resistor allow you to identify what resistor this is. So for example, the first one is green. So you look at the chart. Okay, what is green on the chart? Okay, green represents 5. So you know that the first digit is 5. The second is brown. What does brown represent on the chart? Okay, brown is 1, so you know that we have 1. So the second number is 1. The third one is red. Now, since this is a 4-band resistor, the third band is going to be the multiplier. So multiplier just means the number of zeros, right? So we have the color is red. Red represents 2. So the multiplier is 2. It just means that we have 2 zeros, correct? And the tolerance is gold, which is 5%. So if you look at this, what is the resistance of this? Of course, it's 5.1K. 5,100. We can just write as 5.1K. Let's do this example here. So we have gray, red, and yellow. What is gray and red? Gray is 8, red is 2. So I'll put down this as the first and second number. So we have 8, 2, and then the multiplier is yellow, and that tells us the number of zeros. So yellow corresponds to 4, so this is 4 zeros, right? 1, 2, 3, 4. So what is that number here? If we say, okay, how many thousands? We have 820,000. So we can write this as 820K, right? Of course, here we have, if you look at the color right here, it is not gold, but it's silver. So it's going to be plus or minus 10%. 10%. So gold is 5%. Silver is going to be 10%. Let's look at the last one here. Brown, black, gold. So brown is going to be 1. Black is going to be 0. And here we have gold in the third in the multiplier. And so when we have gold in the multiplier, when we have gold in the multiplier, this is actually letting us know that we need to instead of adding 1 0, we need to divide by 10. So when we divide this by 10, we're going to get 1. So this is how we get 1 ohm, right? So again, you can see it right here. For gold, it's going to be 10 to the minus 1. So the multiplier for gold is going to be 10 to the minus 1. So this is divided by 10. Now let's come to the end of this. So of course, there are other ways that resistors are identified. So resistor color code is one way that you can look at your component and see what the value is. Some other resistors, they have some other conventions for finding the resistance. We're not using these here. This is what some other resistors look like. This is called a potentiometer or rheostat. So it's a variable resistor. You can see here, we have the symbol here of a resistor. So this is the symbol for a resistor, but this has an arrow on it indicating that you can change the resistance. And that is done by essentially turning the wiper blade. So if you look at this, is the resistive element, and the length of it is here, right? That's the total resistance. But when you have the selector blade pointed here, you are only getting the resistance from here to here. And so the resistance is based on length. Since you can change the length by turning this section right here, you can actually change the resistance from 0 to the maximum when you measure across these two here. So what is a circuit? A circuit, we said, is a closed path for current to flow. Closed path for current to flow. Now we said current has to do with the movement of charge, right? And we said that what are the charge carriers? The charge carriers are actually the electrons, right? So what is really moving in the circuit is actually the electrons are moving. All right. Now let's have a look at the meter. So again, we have a digital multimeter that we're using in the class. Now the meter can measure current. It can also measure voltage. It can also measure resistance. So to use the meter, we have to configure it to measure this thing. So if you look on the meter here, you see that we have a section for voltage. So this is voltage, and this looks like a wavy line. So this is like AC voltage. This one looks flat. So this is for direct current. So this is one we'll probably be using. We'll be using this DC voltage. And we'll also be using current as well. We'll be using current, and we're going to be measuring resistance. I don't see it on here, but definitely we'll be measuring resistance as well. So how do we use this meter? We need to configure it. Okay. How do you configure the meter? We'll talk about this more in the lab, but let me just show you this. To configure the meter, so this will be repeated in the lab. To configure the meter, you need to change the setting. We need to make sure the setting is on whatever we want trying to measure, and then we need to see if you need to change the probe location. So there are different probe locations on the meter to measure the different things. And so what are we measuring? So if you want to measure voltage, we need to make sure that the meter setting is on V for direct current. Most times it has a line. And also we need to make sure the two probes are going to be on common, and the other one is going to be on volt ohms most times. If you want to measure resistance, similar. The setting needs to be on ohms. Most times it has the symbol ohms, and the two probes of the meter are going to be on common and on volt ohms. Then if you're measuring current, most times the setting, we're going to be measuring a very small current. So instead of just being on current, we're going to be on milliamps or even microamps. Some meters just have ampere DC. And of course, for the setting here, we're going to be in common, and we are going to be, there's a special milliamp port on the meter, or microamp port. That's what we'll be using. So there's a special circuit to measure current. And so we'll make a note of that when we use the meter in the lab. So as we end here, just remind you of safety. We need to recognize safety hazards on what to do in an emergency, and we talked about that in the lab. Some key ones, we have electrical shock. This is, you should know the location of the emergency shutoff. Know and follow the safety rules in the lab. Electrical safety. Identify where your fire extinguishers are to put out electrical fires, and be aware of burn hazards with jewelry. So again, that's one of the rules you'll see when you do your lab. When you're working on your circuits, you need to remove jewelry, because when you wear the jewelry, it provides very low resistance for current to flow, and so a higher current can enter your body through your jewelry than through your skin. Not only that, the jewelry, normally behind the jewelry, is very moist, and also that lowers the resistance of your body. Then also keep a neat work area.